Okay. Oh, there's only 45 of us. No. Okay, so I hope everyone can hear me. If you cannot hear me, please let me know. And I hope everyone can see my screen. Okay. Yeah, this lecture is recorded, and hopefully after we finish, then I can upload this to YouTube, for example. Then probably you can watch this video, provided that it's not corrupted. Okay, sometimes things happen, and yeah. Okay. So okay. So let's continue with this slide. Okay, which is double integration in polar coordinate. So let me use the full screen. Okay, so there are a lot of topics here. We've seen a few slides last time. So this is polar region. Okay, when you have something like this, for example, so most probably you can describe this easier by using polar coordinate rather than using rectangular coordinate. For example, this is when you use rectangular coordinate. Okay, you have this, which is the line here, and you have 0, y greater than or equals to 0, which is this line here, and your x from 0, which is the line here, and then you move it to the positive x direction until you reach x equals to 2, where your y upper and lower boundary essentially coincides. Because when you substitute 2, I mean, here you get y less than or equals to 0, y greater than or equals to 0, which means y equals to 0, which is here. Okay, but which means that this is a constant, this is constant, but here is a function. But when you use polar coordinate, everything is constant. Okay, this is constant, this is constant, this is constant, this is constant. Okay, which means that it's probably easier to use polar coordinate when you have this kind of domain or region. Okay, or if your integrand, I mean, when you do the integration, there's an integrand in the middle of the term. Then if this term involves something like x squared plus y squared, it's probably, easier to use polar coordinate. Okay, but it depends. I mean, on certain, on the whole thing. I mean, your integrand, your limits, and so on. Okay, so we've seen this last time. Okay, we have something like this, simple polar region or simple region in polar coordinate, in which you just need this boundary and this boundary to be constant, while this boundary and this boundary are constant or function. It's okay if it's function, which is like this, r2 theta and r1 theta, but this one here must be constant, and this one here too. Okay, so a simple polar region in polar coordinate system is a region that's enclosed by two rays or two lines that correspond to theta equals to alpha, which is here. Remember, theta is angle measured from the positive x direction here. Okay, and theta equals to beta, which is the angle measured from here to here. Okay, and two continuous polar curve, r1 theta and r2 theta. So remember that r is the radius measured from the origin or the pole. Okay, so you learned before with Prof. Anwar. Okay, so the origin is also called pole. Okay, oh, hang on, let me take this. Okay, so you have something like this. I'll just put it here. Okay, so R, it must comes from here, from the origin, or sometimes we call the pole. Okay, so alpha measured from here, beta is measured from here, I mean counterclockwise. Okay, so R1 theta, okay, let's say you have one line here, which is something like this. And the value is, let's say this is theta equals to theta 1. Okay, so your R1, sorry, your R here is called R1 T1, and this is R2 T1 because your angle is theta 1. Okay, but I mean similarly, if you have, for example, here, theta from, I mean, equals to theta 2, then here will be R1 theta 2, and this is R2 theta 2. So in this case, or in general, R1 and R2 is the distance of this point and this point respectively to the origin, to the center. Okay, it's not the position. With position, you need to convert it. Let's say you are given R1 and let's say this one theta 1, for example, or whatever name that you want to use. Okay, so in this case, R1, I mean, this is probably a recap of what you've learned before. R1 is the, sorry, theta 1 is the measure or the distance from the pole or the origin. Sorry, I need to use different color for this. Okay, it's the point here, and then this is the theta 1, and the distance from the pole or the origin to this point is R1. Okay, so R1 and theta 1 doesn't give you directly the coordinate, because if you want the coordinate, you need to convert it, which is x equals to r cos theta. In this case, it would be R1 cos theta 1. Let's say, let's name it x1, and then y1 equals to r sine theta, which is R2 cos theta 2. Okay, so this is probably a recap of what we did before. So it's like here is x1 and here is y1. Okay, so you just need to remember that r is a measure of distance from the point, I mean from the point or from the origin to the particular point or the point that you focus on, and theta is the measure of the angle between this point to the, or from the positive x direction or axis, sorry. Okay, so sorry. A simple polar region is a region that is enclosed between two rays and two continuous polar curve, r equals to r1 theta and r2 theta. And so r1 theta and r2 theta can be constant, it can be function, doesn't matter. Okay, So the equation of rays and the polar curve satisfy the following conditions, which are, number one is alpha must be less than or equals to beta. And the angle of alpha must be less than or equals to beta. I mean, it's like what you did before when you have limits on integration, one must be greater than the other. And okay, and then beta minus alpha must be less than 2 pi, which means that if you have, because one complete cycle is 2 pi, okay, so you need to be less than that. I mean, less than one cycle. So let's say you have a point here, and this is P, and then you have, let's use probably this one is theta equals to alpha. Then this condition here tells you that you can manipulate it, which is here, and you manipulate it, you get beta must be less than alpha plus 2 pi. Okay, which means that I think this is beta. Sorry, this must be beta. Okay, now correct. So if you have, for example, beta here, I need the ruler, where the angle is measured from here as usual. This is still okay because beta minus alpha is less than 2 pi, or beta, not alpha. Which is beta less than alpha plus 2 pi, which is here. One complete cycle is 2 pi, which means that if you increase beta from here until here, then let's say this is your beta, then you have beta equals to alpha plus 2 pi, which is what you don't want actually. Okay, in general, you just take beta to be greater than alpha, but it cannot be greater than alpha by 2 pi. It must be less than 2 pi. I mean, if it's here, it's alpha, so it can be greater than alpha, probably up until here. I mean, as long as it's not alpha plus 2 pi. Okay, so nothing special actually. And then the third condition is R1 theta must be less than or equals to R2 theta, and both are greater than 0. Okay, which means that R, as I said, R is the radius or distance measured from the origin or the pole. Then this condition means that the inner boundary must be less than or equals to the outer boundary. Okay, so something like that for all value of theta. Okay, so condition 1 and 2. Okay, as you can see here, the ray theta equals beta can be obtained by rotating the theta equals to alpha counterclockwise to an angle there at most 2 pi radians. Okay. So which means that you can take it until here. There's no issue. Okay. And condition 3 says that this R1 and R2 here they can touch, but they cannot cross over one another. Okay. So if you have something like this, your R2, and then somehow you have R1, something like this. So there's an intersection point, which is here, and there are value of theta, which is from here, where R2 greater than R1. Remember, R1 and R2 and any R is actually the measure of the distance from the origin. So in this case, this is not, I mean, this doesn't satisfy this condition, okay? In terms of the region to be simple polar region. Okay, and then there are other remarks. Okay, so as you can see here, the graph, I mean, all figure A, B, C, the graph R1 and R2 do not cross. Okay, this is your R1, this is your R2, and this is R1. The R1 is actually a point, and this is R2, and this is also R1 is the point, and R2 is the outer boundary of the region. Okay, so if R1 equals to 0, then the boundary reduced to a point or the origin, the whole, which is here. So in this case, your R1 is 0. Okay, remember, R is the distance. And then if beta equals to alpha plus 2 pi, then the rays coincide, the line coincide. If this equals to this plus 2 pi, then you have the same line actually. And then the boundary curve R1 theta here is called the inner boundary of the region, while the curve R2 theta is called the outer boundary. So this is nothing special actually. Okay. And then this is simple polar region, as we discussed just now. Only the two angles here need to be constant. Okay. So it's like, but now we have polar rectangle. Okay. So it's like before this, you have something like this. Hang on, I'm afraid I'm disconnected. I hope everyone can still hear me. Okay. Okay. Okay, so this is, let's say this is your domain R. Oh, sorry. And you have this is X, this is Y, this is A, this is B, this is C, this is D. So you have a rectangular domain. Okay. So this is, sorry. This is analogous to, I mean, the polar rectangle is here is analogous to this figure here. Okay, which is the boundary of the region are all constant. In this case, you have x to A, x equals to B, y equals to C, y equals to D. Okay, but in this case, you have, oh, sorry, here you can write it. Okay, R, x and y, such that x from A to B, y from C to D. Okay, so in this case, it's the same. Okay.
Understood.
Sorry? Ada soalan ke? Okay, so you have R. So in this case, your region here. So I'll just I think I'll take this and put it in here. Okay, so here your boundary. Oh, sorry, what happened? Okay. This boundary here comes from this line, this ray, which is theta equals to pi over 6. And this boundary here comes from this line. Okay, this line, this is the origin. And the line, this line is theta equals to pi over 6. Pi over 4, sorry. This boundary here comes from part of this, come from the circle. Here is actually, but it's okay. Okay. And the circle has radius 1.5. And the outer boundary here is actually part of a circle with radius 2. Okay, so you can combine all these numbers to form your region R. So in this case, you have R. Oh, sorry, I use black pen. You have R theta such that then use okay R from 1.5 to 2 and theta from pi over 6 to pi over 4. So you need to make sure that this must be less than this and this too. Okay, I mean the one here is the lower boundary and this is the upper boundary. Okay, so it needs to be correctly placed. Okay, so if I ask you, let's extend this a bit. Let's say we have something like this. I mean something like similar to what we saw just now. Hang on, 1.5 and 2. Okay, I'm sorry because it's not perfectly circular. Let's say this is 1.5, this is 2, this is x, this is y, this origin. Okay, and this is 1.5, this is 2. Okay, so how do you write this in terms of polar coordinate? How do you write this? Can you try probably in 1 minute? 1 minute. Okay. So now here you have you just extend this portion here to the right and in clockwise direction and in anti-clockwise direction until you reach both axes. So what's the equation now? Can you write it? Okay, so easy. So the answer is you have r equals to small r theta such that your r is 1.5 to 2 inclusive. That's why you have the equals sign here. And your theta is from 0 to what? 2 pi. Sorry, pi over 2, which is 90-degree angle. Okay. Okay. So let's say you have something similar. Probably or probably slightly different. Okay. Oh. Okay, let's assume that this is a perfect circle, a perfectly circular shape, although it's not really a circle. Okay, let's say it's a circle with radius A. And your region R is everything inside this, including the boundary. Okay, so you denote it, you name it as as R. Hang on. So what is R in this case? Can you write it? So it will be apa here. What is it? Okay, so it will be R from 0 to A, and your angle is theta from 0 to pi. It's like, I mean, the easiest, probably the easiest way to look at this is just draw a line. It's like what you did last time, something like this. And you move it in the counterclockwise direction. And then as you move this line, you have something like this, something like this, like this, like this, until you finish one cycle. Okay, so as you move your line, your inner boundary always here, and your outer boundary always here. Also for this line, the inner boundary always at the origin or at the pole, and the outer boundary always here at the boundary of the circle, and here too, and here too, even until for every line, okay, your inner boundary always 0 origin, which is what you write here. And your outer boundary always the boundary of the circle with radius A. So that's why you have A here. And your angle, here you start from this line, which is theta equals to 0, and you rotate it, or you move it in anti-clockwise direction until you reach this once again, which means that you completed the angle, and hence you have 2 pi. Okay, so of course you learned this before, and just to make sure that you understand this before we go into integration. Okay, so or actually no, it's okay. No, it's okay. I can add any somewhere. Okay. Okay, so let's see the volume problem. I hope you read this. Okay, so this is actually the same. I mean, similar to what we've seen before. Okay, so you have a volume problem in which you have a surface f, where f is a function of r and theta rather than function of x and y, and then you have your I mean, this is the surface, and then you have your solid generated by the surface on domain R. And the difference between this and what you've seen before is that your region R now can be described, or the region R is described by polar coordinate, which is the left boundary here is theta equals to alpha. I mean, this boundary here. And then this another boundary here is theta equals to beta, and the boundary here is r1 theta and r2 theta here. Okay, so I mean, the difference between this and what we've seen before is the base of the solid, okay, which is r. Okay, and then assume that you divide this r into smaller rectangle, I mean polar rectangle, something like this. Okay. And let's say there are n polar rectangles. There are n polar rectangle here. Okay, so the shape is like something like this, or probably something like this. Okay, the polar rectangle. Okay, here. And then let's denote the area of the kth polar rectangle. Let's take 1, and you denote it. You denote the area as delta A k. Okay? Why k? Because it's the kth polar rectangle. Of course, you can use I, N, and so on. But we use k because it's a ke k, kan? Bilangan yang ke k. The number is k. Okay, it's up to you whether to count this. I mean, whether you take 1 is from here or from this here, this or from anyway. Okay, and then let's this you take this one polar rectangle, and then the area is delta A k, and then let's take a point in this region or sub region here. So this point can be denoted by RK star theta k star. Again, k because it's the kth polar rectangle. Star is just to denote that this is a specific point that you take. Of course, you can take point from this corner, this corner, this corner, or this corner, or from any part of this polar rectangle. So you just take one, and we denote it with star. Okay, so as shown below, the product of the height of the surface at this point, I mean, you have the surface, FR theta, you evaluate it at this point that you take here, RK theta, sorry, RK star theta K star, which is here, you evaluate it, you get this one, and you multiply this height with the base area, which is here, delta AK, then you get the volume, right? So we learned before in school, for example, the area of prism or cuboid, for example, can be found by multiplying the base area and the height. Okay, so it's something is similar. Okay, but now of course your area is not perfectly shaped. Okay, so the volume of the solid V, this is your volume, the solid. You can get it by creating a similar prism, okay, like this, okay, whose base actually comes from the squares here, or rectangles, rectangular region here, and then you add them. You calculate one by one, and you add them, something like this. Okay, the summation of the volume of each polar rectangle, sorry, polar, what we call it, polar prism or rectangle or so on. Okay, just add it. Okay, once again, the volume of the solid is actually the summation of each prism here. Or sometimes I use polar prism, or sometimes I call it polar rectangle. Okay, I mean this the name probably a bit. There are a few names for it, so hopefully it doesn't confuse you. Where n is the number of polar rectangle, but we don't really care about the n as of now. Okay, so in general, we know from before we learn, and even from school, we learn that as we increase the number of polar prism, the number of prism here, okay, which means that when we increase the number of prism, which means that you have more polar rectangles here, which means that the size of each polar rectangle becomes smaller and smaller, then you get better approximation of the volume of the solid. So the limit of the summation, or the limit of the Riemann sum or polar Riemann sum, is actually the volume of the solid. And if this limit exists, it actually can be represented by double integration of f over r. And here is dA. Okay? So, of course, as we learned before, the integration here will only give you the volume of the solid generated if the integrand is continuous and non-negative. Okay, so we learned before, if there's a negative value of f, then you don't get the total or the actual volume of the solid. Okay, so so you can read it here. So it just similar to what we learned before. Okay, but at the moment we assume that our integrand is always non-negative, so that we can always interpret 2 as a volume. Okay, but here there is a new thing, which is here we know delta. I mean, in Cartesian equation we have delta A K, or delta A. I mean, to make it easier, you just remove the A. Delta A equals to delta x times delta y, or you write it dA equals to dx dy in rectangular or Cartesian coordinate. But what is delta AK here or here in polar coordinate? What is it? Okay, it's not like the delta r times delta theta and so on. Okay, there's some way to determine it. Okay, so here you can read it how I mean, this is actually taken from the book, and this actually can as you, I mean, if you try to do it, you will get here delta AK, which is here, is actually equals to delta R, which is the change in the volume, which is here, the difference between the inner boundary and outer boundary, and delta theta. I mean, just ignore the K, because K just indicate the position. Okay, delta theta is actually the difference between this angle measured from positive x direction and this angle, which is delta theta. And not only that, we have to multiply this with R. And then this is actually represent the area of here. Okay, which means that the important thing is that if you want to do integration using polar coordinate, something like this, I mean, this is the general formula. Okay, you have your integrand f, but dA now is a r dr d theta. So there's a r here. You always need to multiply your integrand with r. Okay, so we'll see a few. I mean, there are a lot of examples actually in this slide. Okay, so the key here is that the integrand must be multiplied with r before you do the integration. Okay, so this is how to determine the limits of integration for a simple polar region. As I said, you start from here, and then from, I don't know, from here is okay, and you move it in anti-clockwise direction, and you get the boundary for each line. Okay, so that determines your limit. Okay. So going back, no. Okay. So let's see the example here. I mean, it's quite long. Yeah. Okay. So let's try to do one very simple example. I mean, before we go into discuss this example, let's take one simple example, probably example 0. Oh no. Oh, sorry. One more. Okay. Let's try example 0. Okay, let's say you have a circle. It's like the quiz we had last time. Okay, So you know, this is the position, a minus a, and so on. This is x, this is y. Okay, so you know, when you do integration, the formula is like this. Let's say this is your r, and this is your f. I just write f, and this is your dA. F, it could be, of course, fxy, or in polar coordinate, if fr theta. And we know the relationship between r theta and x and y. Okay, so this is quite, let's say I ask you to do integration. Let's do integration. Okay, try to integrate with your f equals to 1 dA, okay, where r is the circle shown on the left, which is here. Okay, so I ask you to integrate, to do double integration with your integrand 1, your f equals to 1, okay, where r is the circle shown here. Okay, so let's write r first. Okay, so r, okay, so you can draw a line here. I mean, if you still can't see it, just draw a line here and move to this direction, which means that you have something like this, something like this, something like this, something like this, maybe something like this. Okay, so your inner boundary always 0 for each theta, and your upper boundary always r equals to a for each value of theta, which means that your r is from 0 to a, and your theta is from 0 to 2 pi. Okay? Which means that here, oh, hang on. Let's say you want to do integration. Let's say you want to do dr d theta. Okay, so you need this one, and then dA is actually r dr d theta. It's actually, it could be r d theta dr, or something like this. Okay, so let's say you want to follow this, which is this one. Okay, so since this is r, so this must be r, this must be theta. So your theta is 0 to 2 pi, r is 0 to a. And then you continue the integration. Oh, hang on. Okay. Here you get r squared over 2. This is 1 over 2. Here you have r squared. This is a, which means that a squared minus 0 squared. Okay. Which is half this 2 pi a squared d theta. A squared doesn't depend on theta, so you just bring it out. Integrate 1, this is 1. You get 1 in respect to theta, you get theta 2 pi 0, which means a squared 2 times 2 pi, you get pi a squared, which is the area of the circle. So it's actually the same like what we did before. In order to find the the area of your region R, regardless of the which coordinate system that you use, df must be equals to 1. Okay, that's why I asked you to integrate when f equals to 1. But the difference is now your dA is not dx dy, but it's r dr d theta. Of course, you can change to r d theta dr. And then if you do r d theta dr, then the limit also need to be changed accordingly. Okay, so you can see here there's no substitution like what we did in the class last time. It's just a simple integration. Most of them are constant. Okay, so this shows that when you have a circular kind of region, then it might be easier. It could be easier to use polar coordinate in your integration. Okay, so let's take a break. Now 3:51. Okay, let's take a break until 4, and then we try to continue with example 1. Okay. If you have question, you can write it in the chat box here. Thank you. Okay, Assalamualaikum warahmatullahi wabarakatuh. And hi once again. Okay, so let's just recap of the things that we discussed. Okay, let's say you have a function f, and this function can be written in Cartesian coordinate, of course, and probably in polar coordinate. And you know, this is actually interchangeable probably most of the time, if not all the time. So, but because the relationship that they have here, where x is equal to r cos theta and y equals to r sine theta, and of course r squared is equal to x squared plus y squared. So, I mean, probably in general, let's write it as f. Okay, so let's say you are asked to do integration of integral f over region R, and I write it as dE. Okay, so in Cartesian coordinate, we write it as f xy, or it's okay to just write it as f, and dA is probably dx dy, which means that here will be x, here will be the limit for y. Okay, and so this is Cartesian. For polar coordinate, f, okay, which is fr theta or f in general, okay, I mean, it's actually similar. So dA is r dr d theta. So if you take something like this, so this will be limit for r, this is limit for theta. Okay, of course, you can change the order of the integration. Here, which is dy dux, and here is d theta dr, but you also need to change the limit here. Okay, so in terms of, I mean, this is the general form of the double integral. And this is how you do it in Cartesian, and this is how you do it in polar. Which is polar, you have the r. And don't forget this. Quite many times, students they just forgot to write this in the exam, I mean in final exam. Okay, so just don't forget this. Okay, so just add r here, and everything else is actually the same. Oh, sorry, not this one. Okay, so let's have a look at this. Okay, the region R is an annulus. Okay, annulus is like a donut. I mean, annulus is a donut. Okay, something like this. You have a hole in the middle. Okay, this is formed by two circles of radius 1, which is you have the inner circles here, which form the hole actually, and the other circle, which is square root of 5, is its radius, which is here, and just a little bit more greater than 2. Okay, so you have the region in between these two circles, which is called annulus, that you want to integrate, or you want to do the integration on. Okay, so you are asked to do this one. Okay, so let's take this. Okay, oh, hang on. Oh, go to the next page. Okay, something like this. So you draw a line from theta equals to 0 from here, and you move it in anticlockwise direction. Here, you always get a line. Oh, sorry. Here, who's actually coming, which is coming from the origin. So you have something like this, and actually is like this. I'm sorry because it's not really accurate. I mean the drawing here. So you have like this. Until you finish this. Okay? And for every angle of theta, you start from here, theta equals 0. Oh, sorry. And you finish it at theta equals 2 pi in order to complete to get a complete circle. Okay? So for each value of theta, let's say this is theta equals to, I don't know, probably pi over 6, which is 30 degrees, or probably slightly more. Okay, you have your inner boundary. What color? Here, which is 1. And your outer boundary is r. This is r equals to 1. This is r equals to square root of 5. And this is actually true for every line that the inner boundary is r equals to 1, where r is actually the distance measured from the origin, and the outer boundary is r equals to square root of 5. Okay? So your r here is from 1 to square root of 5, where your angle from theta to 2 pi. Okay? So if you have, sorry, so if your theta is from, for example, 0 to pi, everything else is the same, you only get the upper part of the annulus. Okay, so theta determine actually the cycle. Okay, so in this case you have your r, and then you want to integrate this. Okay, so let's do the integration. Hang on, what happened? Copy the clipboard. Okay, we have this. So this is your f. Okay, so the formula here, you just use it. Okay, now dA change to r dr d theta or r d theta dr. It's up to you. Okay, provided that the numbers must be, I mean, you must use constant for the limits of the outer integration. Okay, so here you have this one, x equals to r cos theta. Y is r sine theta. Just put it in a bigger bracket. dA is r dr d theta. So this is r, which means this is r, this is theta, and you know your r here from 1 to square root of 5, and your theta here from 0 to 2 pi. Okay, so just expand it. Square root of 5, you have r squared cos theta squared, and then yeah, don't forget you have this. Just you need to multiply this with r, so you have r cubed, and you have here r squared sine theta dr d theta. So this r here becomes part of your integrand. Okay, so you have this, and then You just follow this, okay? You integrate it, so you have something like this. Integrate with respect to r, which means now you have r over 4, sorry, r to the power of 4 divided by 4. Cos theta squared is a constant because it doesn't depend on r. And then r cubed over 3, sine theta doesn't change because it doesn't depend on r. And then you evaluate, substitute this r value into r, you get something like this. And you try to simplify things. You have sine with certain complex look multiplier, but it's okay because it's constant, so it doesn't change anything. And here you have cos theta squared. And you know, when you have cos theta squared, you need to use the double angle formula, which is here. Okay, and this is, you doesn't change this, so just maintain as what it is. And now you integrate, I mean, you simplify this, since you get 3 cos 2 theta plus 1 times 3, 3, and this is actually the same thing. And now, easier to integrate cos 2 theta, integrate, you get sine 2 theta over 2, which is here. Okay, and here sine theta, you get minus cos theta, which is here. Okay. Oh, sorry, and then here you get 3 theta. Which is replace everything, and you get 6 pi. Okay. Okay. Any question up until this example? You can ask if you have question, or you can type if you don't have a microphone, or you just like to type, just type. Okay.
No, sir.
Yeah.
No question.
Oh, no question. Okay, I'm quite surprised because there's only 58 students here. Okay, because actually we supposed to have 154. No, 154, so more than like 100 students, which they do not count. But it's okay. Okay, so let's have a look at this. Evaluate the double integral here. So dA is here, of course, is r dr d theta, or r d theta dr, it's up to you, and sine theta. And this is your r. Okay, where r is the region of the first in the first quadrant. Okay, this is first quadrant. I mean, theta equals to 0 until theta equals to pi over 2. It's first quadrant. This is second, third, and fourth. You learned this before. Okay, so evaluate this, where r, I mean over r, where r is the region in the first quadrant, that is outside of the circle r equals to 2. And inside the cardioid, r equals to this. Okay, so here they just use r equals to 2 to represent the circle. Okay, but before this, hang on, we use slightly different notation, like here. Okay, so here is the region R, where R is from 0 to A, inclusive of the endpoints, and theta from 0 to 2 pi. Okay, but here, I mean, this is the region, but here it tells you that your region is inside the circle. So this is R, sorry, outside the circle. Okay, so it's like this. If you have something like this, okay, good. I'll take, oh no, let's say this is your A, Okay, so if I tell you R equals to A, okay, we know that R is the distance or radius, okay, from the pole or the origin. So R equals to A is actually only this line, only the boundary of this circle. But if I told you that R is less than or equals to A, it actually includes the boundary and also the points inside this boundary, because R is the distance from the pole origin. So the distance can be equal to 2 or can be less than 2. For example, the point here. Okay? The point here obviously has the distance between this point to the radius or to the pole is less than A, which means this is fulfilled or satisfied. Okay? So when R equals to A, it just gives you the boundary. But when R equals to or less than A, it gives you the whole region, the whole thing. Okay? And of course, you learned it before. I mean, if you have, for example, I don't know whether I can move the line here. If you have the region without the boundary, then it becomes R less than A, something like that. Okay? So in this case, I mean, in all of this, okay, or even you can have one more thing, okay, which is here, but you don't really interested in the region inside the circle, but you are interested in the region outside the circle. And so this is R greater than or equals to A. Okay? So in all these cases, you actually don't mention theta, right? There's no theta in this equation, in this, and this, because it's like what we discussed before. For a circle, a cylinder. A cylinder is a 3D shape, but it uses equation for circle, which is a 2D shape, because regardless of the height of the cylinder, the equation of the circle is satisfied. That's why you don't need the z for the equation of cylinder n. I mean, like if you have a cylinder with radius a, you just use this equation. There is no z in your equation because this is always satisfied regardless of the value of z. Okay, which means that if you have a circle or something like this, the shape or the region like this, it's probably okay to disregard this. Okay? Because this is always satisfied for any value of theta. But I would advise you to write it. I mean, just for completion. Okay. If you have a circle, write both the r and the theta. At least it helps you to write the limit of the integration. But if you don't have it, it's not. I don't think it's wrong. Okay, still acceptable. But I would advise you to write it with right theta. Okay. Then okay, something like this. Let's go back to our example. Okay, evaluate this one where R is a region in the first quadrant outside the circle R equals to 2. Okay, you have this R equals to 2. Okay, so this is actually this point, this thing. Okay. Outside the circle r equals to 2, and inside the cardioid, okay, this is your cardioid. Okay, something like this. Okay, so you need to, I think, I don't know if Prof. Anwar told you before, you need somehow to remember this, I mean the shape. Okay, if you can't, yeah, you need to remember, I think. But sometimes, I mean, if, I'm not sure, probably you'll be given the figure here if it's too complicated. But I mean, for your own understanding, I mean, you can try to, I mean, probably you can use software, for example. I'm not sure if I have it here. I asked you before to install CHMath. Okay, I know. Okay. So this is my CHMath. It's actually Python extension. You can try. I'm not sure if I remember the code to draw this. So let's say I have R. No, I have a variable R. Hang on. Oh, yeah, theta. Okay, and I have a function here. R equals to 2 times 1 plus cos theta. And I want to plot this. So just do, I think, polar plot. I'm sorry if I can't, if it doesn't produce any plot. And I want to plot using polar coordinate R, where R is this function here, for theta from 0 to 2 pi, and I enter, and I get something like this. Okay? Okay, so if I use the domain from 0 to pi, I get half of the cardioid. Okay, so this is actually from CHMath that I asked you to install, although it's not compulsory. Okay, and in fact, if I'm not mistaken, I can try, for example, let's say this is my R1. I mean, sorry, let's clear all this thing. Okay, let's say I have two plots here, and my R1 is the cardioid, so which is actually the same equation. And my R2 is the circle here, and I can plot it. Let's say I name it P equals to polar plot for R1. And then I have another one, which is R, no, hang on. I just forgot. Okay. I need to correct the boundary. Okay, let's say P, I name the plot as P, which is a plot in polar coordinate of R1, which is this function, where theta is the domain, I mean, is the variable, independent variable from 0 to 2 pi. Okay, so I enter, and then I create another plot for this circle. So I just plus equals, I think you've seen this before in C++, and this is for R2, which is actually a constant here. And then I show, I think, I'm not sure whether this is correct or not. Okay, I get this. Okay, this is R equals to 2. This is R equals to the cardioid. Okay, of course, there are techniques to shade this region, but I think it's not I mean, it's not needed here. Okay, so you can play around with this. I mean, with CHMath, it's quite good. I like it. Okay, so okay, let's go back to our example here. So you have the intersection here. Okay, from here you can draw the region here, And then what you need to find, I mean, it's quite obvious that you need to start from theta equals 0 until theta equals to pi over 2. Okay? It's quite obvious, but you can check. Okay? Where you try to find the intersection between these two polar curves. Okay, oh, sorry, happened. Okay, find the intersection. We have first polar curve and the second polar curve. You can find it by equating it. Okay? This is the first equation. Sorry, this is this equation, and r equals to 2 is another equation, and you solve it. Okay? You get theta equals to pi over 2 and 3 pi over 2. This is pi over 2 is 90 darjah is 90 degree. This is 270 degree. And it's true because as you can see, there's an intersection here and there's an intersection here. But you don't really care about this second intersection because it doesn't included in the first quadrant. Okay, so first quadrant is here. So you just concern on, we have concern on this one. Okay. Okay. So, I mean, let me try to write it here, the intersection. So you have r, hang on, 2, 1 plus cos theta equals to 2. Okay, I mean, for those who don't know, this is, let's manipulate, and you get cos theta equals to 0, which means the theta equals to inverse cosine of 0, which is, you know, pi over 2, 3 pi over 2, 5 pi over 2, and so on. In fact, you can have pi, and I think 2 n plus 1, I think, where n can be plus minus 1, plus minus 2, plus minus 3. N, something like that. And it can be 0 too. Okay, but you take only one. And then, so the integrand, okay, this is what you want to solve. Okay, so let's take this. Hang on. Oh, sorry. You take this. Okay, draw a line starting from theta equals to 0, which is this line. Oh, hang on. This line here. Move it to the, oh, hang on, anti-clockwise direction. Move it in anti-clockwise direction, and you get this line. Oh, hang on. I always forgot the ruler. Right? But it must be a radial line. I mean, the origin must be the center. Okay, something like this. Okay. Okay. So for all this line, okay, your inner boundary is this one. This one, this one, this one, this one, and this one, this one, and this one. So your inner boundary always r equals to 2. And your outer boundary, which is this one, this one, this one, this one, this one, is always r equals to 2, 1 cos theta. So your r in this case is r from 2 to 2 times 1 plus cos theta. And your theta is from 0 to pi over 2. Okay, from this, which is theta equals 0, until this, which is theta equals to pi over 2. Okay, I hope you can understand it. And how do we know that it's pi over 2? We we find the intersection, and it gives us theta equals to pi over 2. So our integration becomes this one here. Let's take it. Oh, sorry. Okay. So here, sine theta is good because it's already in polar coordinate. dA is r dr d theta, or dr d theta, it's up to you. So this is r, so this must be r, which is from 2 to 1 cos theta. And this is theta from 0 to pi over 2. If you can see here, if you take dA equals to r d theta dr, you will have a problem, because you will integrate with respect to theta first, where it's no problem here because you have 0 to pi over 2. But later, if you want to integrate dr, then r is actually a function here. Okay? So you cannot have a function as your limits in the outer integration. Okay? You cannot have this. So this is not right because you have function here, which means that you won't be able to get a number from this integration. You won't be able to solve it. Right? So that's why you use dr d theta instead. Okay, and then you solve it here, integrate with, because this is theta, it doesn't depend on r, so just put it out here. And you have this one, which is r squared over 2. I put 2 here outside, substitute, and multiply, I get this. And this is easy, because this is cos 3 theta divided by 3, multiply with minus here. And then this is cos 2, cos squared divided by, oh no, so there's no problem, divided by 2 times 2, so there's no multiplier here, and you get this. Okay, so this is quite easy. Okay, now you probably have something quite complicated. Okay, it gives you, rather than it give you a picture, a 2D picture, now you have, sorry, 3D picture or 3D setup. Okay, so here the sphere of radius A centered at the origin is expressed in rectangular coordinate as this. This is the equation of a sphere centered at origin, radius A, and hence its equation in cylindrical coordinate is here. Okay? I mean, like, you just replace this x squared plus y squared with r squared, and z just maintain here, and a is just the same thing, the same a here. Okay, so you'll learn cylindrical coordinate later. Okay, and then use the latter equation, which is this equation, and a polar double integral to find the volume of the sphere. And so here, as you can see, before this, I mean, for example, this first example, we try to find the area of a circle, something like this, with radius a, and we can quickly solve it and get pi a squared. But now you are asked to prove that the volume of a hemisphere is equal to, we know the volume of sphere is pi over 3. Sorry, pi over 3. What is it? 4 over 3 times pi a cubed, where a is radius, which means that the volume of the hemisphere, whether it's upper hemisphere or lower hemisphere, is half of this, which is 4 over 3 over 2, which is 4 over 6. pi a cube. Am I right? So that, okay, it just tell you, I mean, the question just asks you, I mean, use this equation and a double polar coordinate to find the volume of the sphere. They just ask you or tell you to find the volume, but actually we learn from schools that the volume is this, hence we know that we need to get this when we do the integration. Okay, it's like proving the formula that we've there's a accepted by people. Okay, which is this. Okay, so we have our hemisphere. So just take this. Okay, so although it's given, actually we can derive it. I mean, actually even if you don't have this equation, you must be able to solve it because you already learned how to write the equation for sphere. So equation of a sphere is x squared plus y squared plus z squared equals to a squared, for example. And you can manipulate this term and you get z equals to plus minus square root a squared minus x squared minus y squared, where the positive give you the upper hemisphere and the negative give you the lower hemisphere. It's like a upper circle and upper semicircle and lower semicircle that you learned before. Okay, so how to integrate, how to find the volume of this? You need to first find the radius. Sorry, not the radius, the region R, which is the base of the hemisphere. Okay, so R is, what is it? R is actually when z equals to 0, which implies that this equation becomes a circle, an equation of a circle. Can, because there is no z. Z now is 0. It gives you a circle. Okay, so in polar coordinate, you can write a circle as this, where r from 0 to 2, sorry, not 2, a. Hang on. And theta is 0 to 2 pi. Okay, because you've seen this a few times today. Okay, so this is actually the equation for this. Okay, so when you want to find the volume, so just write the full equation. Integrate over r. This is your function. This is dA. Okay, now what are the limits? So here, let's write dA as r dr d theta. So r from, just use this, 0 to a. Okay, theta is from 0 to 2 pi. Okay, you are lucky because all their limits are constant. But what is f? F is the shell of this hemisphere, which is actually the z. So here f is the z, but the positive part, which is a squared minus, this is r squared, right? Because r squared equals to x squared plus y squared. So a squared minus, you factorize the minus, you get x squared plus y squared, which means this is r squared. Okay, so you get this. Okay, so hang on, what is it? Okay, so how do we solve this? Okay, we need to integrate with respect to r, right? But as you can see here, you can change the order of integration because there's no theta in this equation. I mean, in the integrand, so you can change it. So you can, oh no, hang on. Let me take this everything here. Okay. Oh, it's okay. Theta equals 0 to 2 pi, and this is 1 d theta. Okay, so I get, this is actually theta 2 pi over 0 equals to, this is 2 pi. And so you have 2 pi, r equals to 0, a r, sorry, I just forgot this, dr. Okay, so here is a squared, okay, dr. So how do we solve this? Okay, so we can try substitution, for example. Okay, let's take in substitution. Let's take u equals the term inside the square root. You're going to replace every r with u. So du dr equals to minus 2r. So when r equals to 0, the lower limit here, you get u equals to, just use this, oh sorry, just use this equation. When r equals to 0, put it here, you get, hang on, get u equals to a squared. When r equals to the upper limit here, a, you get u equals to a squared minus a squared equals to 0. Hang on. So you have 2 pi r0 correspond to u equals to a squared. And r equals to a correspond to u equals to 0. And you have this r, and you have dr, which is actually here, which is du minus half equals to r dr. And from here, you just manipulate it. You bring the minus 2 to the left and r to the right, and you get this. This is actually this one here and this one here. So it gives you minus half du, and this is nothing special. We learned this before. And this is square root of, this is actually u. Okay, so let's go to the next page. Okay, so here the limit is not right because this is a positive number. This is 0. Of course, the bottom limit or the lower limit is greater, so you need to change the limit's position. So what you do here is and multiply with negative, and you have this, and you can simplify this. This is this, and this is minus, and you get pi a squared, and this is u. I just rewrite it as u power of half du, and you get pi, integrate it, you get 3 over 2, 2 over 3, so 0, half squared, sorry, a squared, pi over 3, no, 2 pi over 3. This is u, which is a squared, 3 over 2 minus 0. Okay, so this is power and the reciprocal, and you have 2 pi 3 e 3 So is I'm not sure whether I think it's right. Or 3. Okay, so let's go back to our here. Okay, so this is 2 over 3 pi a cube, and because 4 and 6 is 2 and 3. Okay, which is correct. Okay, so this is how you prove the volume of a upper hemisphere. Okay, by using very little information actually. Okay, is it okay? Or we have if you have, I mean, do you have problem to understand this, or you have question? Okay, as you can see here. But if you try to do the integration using Cartesian coordinate, you will have problem. Okay, because your integrand is this one, right? So you have your, so if you use, I mean, as I wrote there, if you use, hang on, if you use Cartesian equation, okay, hang on, you have this equation for the sphere, and of course you manipulate it, and you get plus minus, oh, hang on, and for the upper hemisphere, you use the positive part. Okay. Now, if you want to integrate using the Cartesian coordinate, you will have the same thing here, which is a circle. I'll just take this. And put it here. Okay. So you need to describe R. Okay. The key here is that how we describe R. Here we use polar coordinate to describe R. Oh, hang on. This one, which is very simple. But now we need to describe R using Cartesian. Okay? We start with a certain line here. Let's say from here, we start with a line here. Oh, sorry, it's not straight. Point here, and then we move it in positive x direction, for example, to this direction. So we have a line here, a line here, line here, line here, line here, until here. Okay. So for every line, the upper boundary always the top or the curve here, and the lower boundary is always the curve here. What is it? Is it just a circle where z equals to 0? So when z equals to 0, we have s squared plus y squared equals to a, which is the same as what we get before this. And so y equals to plus minus a squared minus x squared. So your integration becomes the v is this is the formula, the general formula, but here, let's say from x minus a, I mean from here, s equals to minus a to x equal to a, but your y is this one, the positive and negative part, which is here and here. There's a negative here, but this is positive. And your f is actually this, which is a squared minus x squared minus y squared. Your dA it just follows this, which is dy dx. How can you solve this? If you, I mean, how do you solve this? So probably you can try substitution, but it's a bit hard because there are two independent variables, x and y. Okay, so it'll be something like this. I mean, this is what I mentioned here. Okay. And then please try this. Okay, and this is another question. Okay, we just have about 5 minutes. Okay, here use polar double integration to find the volume of the solid bounded from above by an upper hemisphere, which is the same thing as just now. Okay, but here rather than you given the hemisphere has radius A, but now you have radius 4 because this is 4 squared. Okay? So it's a upper hemisphere with radius 4. And then your solid is bounded from above by this upper hemisphere and laterally from the side by a cylinder. Okay, so you have cylinder laterally as the wall of your solid and the portion of the sphere as the roof of your solid. So from the side, from this direction probably, or from this direction, you have something like this. Actually, I plotted this using Sage Maths that I showed you how to use it just now. Okay, so you have something like this. This is the wall, and this is the curvy, the curved roof here, which comes from the portion of the sphere. Okay, so hang on. So you need to, when you do the integration, of course, you need the R, the region where you want to do the integration on. Okay. So how do you find that? You need to find the intersection between the hemisphere and the cylinder here. Okay, so this is the equation of the hemisphere, which is here. I just factorize the minus, I get this. Okay, and then this is the equation of the cylinder, x squared plus y squared equals to 4, which is the equation of a circle with radius 2 and center 0, 0. Okay, so this is x squared plus y squared equals to 4. I just put it here. So I get 16 minus 4, which is 12. So this is z equals to 2 square root of 3. So the intersection happens when z equals to 2 times square root of 3. Okay? Okay, so actually you don't really, thinking about this one once again, I think you don't really need to find the intersection, because you already, by looking at this, you already know that the region R is actually the base of the circle, of the cylinder. So you can just use this second equation to determine your region R, right? I think so. Okay, you don't need to do the intersection. But hang on, not that the intersection between, I just mentioned about the intersection. Okay, so the intersection is actually the red circle here, which coincide with the circle that represent the base of the cylinder. Okay, so you have this, the equation of the cylinder, okay, which is hang on, x squared plus y squared minus 4 equals 0, which is x squared plus y squared equals to 4. So it's a circle with radius 2, okay, and centered at the origin, of course. So you have this, and this is your R. I'm sorry, because it's not a very good shape. Okay, this is your R, this is 2, this is 2, this is minus 2 in terms of the Cartesian. Okay, but you can rewrite it in polar coordinate. Okay, so this is R from 0 to 2 and theta from 0 to 2 pi in order to get a complete circle or cycle. Okay, so integration, okay, integration is the integrand is actually this, okay, which is the equation of the hemisphere, which is this one. Okay, so to find the volume, we can write it as this. Okay, in polar coordinate, so this is the general formula. In polar is theta from 0 to 2 pi, r from 0 to 2, and your f is the here, and the roof is the portion of the sphere, which is this equation, which is square root of 16 minus r squared, r dr d theta. But for Cartesian, okay, so our v from x minus 2 until 2, y from square root, sorry, ada minus here, 4 minus x squared, 4 minus x squared, but positive, and this is 16 minus x squared minus y squared dx dy. Okay, you can try to solve this. I think it's I'm not sure whether it's doable or not. Okay, but this obviously much simpler. Okay, so I wrote it here. This is for Cartesian and this is for polar coordinate. And here, I mean, of course, if you can recognize it, and this is actually part of the 3 power of 3 over 2, or you can do substitution here. Just take the term inside the square root as your u, and you solve it, and you're supposed to get this. Okay, so please have a look at this. There are a lot of examples. Okay, this is question number 5. It's a bit different. This is you interested in the solid here, but example 5 is you interested in the region here. I mean, bounded by the hemisphere, but from the inner boundary is actually the cylinder. Okay, so you're just interested in the thing here, everything minus the cylinder. Okay, please try to understand this, have a look at this. And example 5 is a bit, sorry, example 6 is a bit difficult to do. Okay, but you can have a look at this. And then there's a example 7. Please try. Okay? You have a few days to study, and this is quite famous example. I mean, like you have a shape, and then this shape is cut by a plane. Okay? Here, and you get a volume. Then you want to try to find the volume in between these surfaces, and I mean the surface and the plane. And then there are a lot of things. This is how you find the area when using double integral in polar coordinate. So I mean it's just the same thing. So you just use the integrand equals to 1, but the integrand, I mean the f equals to 1, but dA is r dr d theta. So it's not. So finally your integrand become r only, okay, not 1, because you have r which comes from the dA. Okay, and this is one of the example. And please try to have a look at this. We will probably select a few examples for the class next week, and then assume that you will learn this your own. Okay, and then this is how you reverse the order of the integration, and so on. And this is, you are given the problem in Cartesian coordinate, but it's hard to solve it directly using Cartesian coordinate. So you need to be able to determine the region R by looking at this, which means that you have to convert this to polar coordinate first before you solve it. Why? Because it's easier to solve using polar coordinate. But the problem is, how do you convert, or how you recognize this, or how you draw this in polar coordinate? That's one of the skills that you need to have. Okay, please try this, because I've already written the answer. Okay, so I think that's all. Thank you very much. Is there any question? Those who have things to do, you can leave. But if you have any question, you can ask. there any question or no? Okay, if no question. Thank you. That's all. Have a great weekend.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you, Doctor.
Okay.
Thank you,
Thank you,
Doctor.
Doctor.
Nak QR balik boleh tak?
Oh,
Thank you, Doctor.
okay. Okay, dah ya? Dah ke? Saya ada satu lagi kelas. Okay. Okay ke yang lain?
Okay, thank you, Doktor.
Okay, sama. Ada lagi ke? Okay, kalau tak ada, let's end the meeting. Thank you.